G'day, Lance from Motive Power, back again with another episode in our series on off-highway vehicle design. Today, we're at EPEC. That's Explosion Proof Engine Company in Western Sydney in Australia. They build explosion-proof diesel engine systems for underground coal and oil and gas applications. Our last episode was about the theory. This episode is about the reality. And we're right up, very close to the hardware involved. Stay tuned. Now, EPEC build engines to oil and gas standards, which is BSEN 1834, and to Australian underground standards, which is AS 3584, Parts 2 and Part 4. And they'll soon be producing the new ISO standard engines to ISO 80079-41. This particular engine I'm leaning against is a coal engine. It's on a dyno, so it looks a little messier, but you'll understand why when we go through it a little bit. Being on the dyno, it has a lot of thermocouples and data logging and instrumentation hanging off it. But yeah, that's part of the test procedure and certification. So way down in here is a Cummins, well, what started life as a Cummins 3.9 litre B series engine. But for underground coal, it gets a few modifications. Firstly, it has a cast iron flywheel housing instead of aluminium, because operators still frown on aluminium underground because of the sparking potential. It's had some serious calibration to fuel pumps, gets a water-cooled air compressor, and it gets a very special cylinder head, one that has more water jackets, a little bit more material, and keeps the surface temperatures down. And it also has a water-cooled turbocharger. And again, that's to keep surface temperatures at a lower level. So it's a Cummins engine, but it's a very bespoke Cummins engine. One of the first things you notice about diesel engine systems is the size of the radiator. This is the stainless steel version, and the whole package we're looking at the moment is configured to go into a PPKME drift runner. We'll show you one of those a little later. But the radiators have to be fairly large, but they have to also be compact. It's a usual compromise because the vehicles are low profile. Bigger than you might think for this 75 kilowatt engine. You've got to remember it has to cool the engine and the exhaust gas and all the water jackets throughout the engine, because everything is water cooled, or nearly everything is water cooled. That's why there's lots of plumbing, and in this case, lots of temperature sensors. And the radiator is a plastic fan, and I'll show you one. This is an aerofoil type fan. The blades are aerofoils, much higher performance than the traditional old brass blades. They've got a twist, they're shaped, and in some ways they're safer. I've actually been next to one of these fans when somebody let a loose hose go into it and the engine was running. The fan disintegrated, but no one was hurt. The shrapnel is quite light and it basically flooded to the ground. I'm not saying you won't get hurt, but it's probably a lot safer and definitely a lot more performance. Behind this fan, this fire-resistant anti-static fan, is the fire-resistant anti-static drive belt as well. So the cooling package isn't that simple. Radiator design is key, fan selection is key, and then even the V-belt, well, it can be tricky too. So let's look at the intake system. Starts right here with a pre-cleaner, and that's important to keep the life of the air filter element as long as possible. Underneath it, in this position, because of the configuration of the vehicle, is a metal housing air filter, a fleet guard unit, no epoxy plastic, a fair income steel unit that will survive. From here, well, travels up and it hits the first strangler. You'll recall from our design video that it's best to have two stranglers. This one here, and then after the turbo, we have another one which is just in here. This one is triggered by excessive airflow. This one is triggered by excessive speed. They're sensed differently and they are different sensors. The turbo in the middle, well, the compressor section is fairly standard. So no water cooling there. After the strangler, we come to the inlet flame trap. This is a spiral wound corrugated ribbon type, and it's removable. You'll see the handle right there. 2 V-clamps, undo it, bring it out, clean it whenever necessary, put it back in. Quite simple. From here, around to the other side, and into the intake manifold, which is this part of the special head. So let's talk about the exhaust system and ignore all of this that's set up for the dyno test. The exhaust system starts on the other side with the water-cooled manifold. That feeds the gas into the water-cooled turbocharger turbine. From there into the first exhaust gas cooler. This unit actually has two, and it does not have a water bath exhaust conditioner or scrubber. In between these two exhaust gas coolers is a plate type flame arrestor, and like the inlet manifold, 2 V-clamps, and that comes out for cleaning. But it is a different size to the inlet flame trap, so that the two can't be accidentally put in the wrong place. If this was an ATEX engine, after this second cooler, there would be a spark arrestor, probably a spark arrestor muffler. But that's not necessary on coal engine, because coal engines, well, the turbos are considered to be spark arrestors. Because this is a coal engine and it's for Australia, the exhaust gas comes down here through this gas box and into a big housing for the replaceable exhaust particulate filter. Now, that's not a requirement under the standards for underground coal engines, but it's almost obligatory in this country because of workplace health and safety requirements. Now, one important point to note is the water cooling. The exhaust manifold is water cooled, so is the turbo turbine, so is the exhaust gas coolers, so is the elbow here. So there's an awful lot of exhaust gas cooling and surface temperature control all the way down to here in the exhaust system. That means there's a lot of heat going in the radiator. And we spoke a little about that earlier, but that drives the sizing of the radiator to a large extent. Unfortunately, the engines we have for our program today aren't fully equipped with the pneumatics, or the unit on the dyno, it's just inaccessible because of all the data log units on it. So I can't really show the control system, the pneumatic safety shutdown system. I can show you some components and parts of it. This is the primary control box for it. And it sits along on top of the engine, horizontal, flat. And that's because this is the area that probably needs to be occasionally troubleshot, and it's positioned in a very accessible position. A particular note is the steel piping, because that means it's very difficult for this safety system to be sabotaged. Where flexible piping, tubing, hosing is required, this is used. Now, it's a wire braided unit, and at first glance you're going to think here it's Teflon with an outer wire braid. It is in fact not a hose, it's a tube. It's a convoluted stainless steel tube, quite flexible as you can see from that diameter, and protected on the outside by a wire braid. Very, very difficult to crush. The problem in the field with rubber hoses in fail-safe safety systems is it's too easy for people to sabotage the system or to override it with a pair of vice grips clamped on a hose, preventing the air from being discharged. And that's a typical thing that happens if it's near the end of shift and the crew are trying to get out of the mine and the vehicle's overheating or is on low oil pressure. The hose gets clamped and the engine blows up. So, doesn't look like much, but that's a major change to flame-proofed engine design. These engines have a lot of pneumatics on them, but simply and easily installed. The intent, of course, is to make it safe and reliable and to sense all the things that are likely to cause a safety issue. Oil pressures, coolant levels, gee whiz, water level in the radiator, gas temperatures, and so forth. For functional safety, here in this state, these units are achieving SIL 2 or PLD, and that's a major achievement. That's typically much safer than the traditional equipment. The way the system works is you put air on the safety system. If everything's happy, that air pressure is maintained, the valves are open, stranglers are open, the fuel is turned on, and the engine will start. It started with a KH pneumatic starter, works great, don't use another brand. And to shut it down, well, if the sensor has a problem, it releases the control air. It's a fail-safe arrangement, loss of air pressure shuts the valves off. The fuel shut-off goes off first, followed by the two stranglers. So that gives the engine a chance to stop because the fuel's been turned off before the stranglers kick in and provide very high inlet manifold vacuum. There is a trick with that because when you start up, you have low oil pressure. So hence the sensor's trying to shut it down. There is an automatic function to provide an override for a short period, long enough to get oil pressure up and allow the engine to run properly. A little bit of smarts that EPEC has put into their control system. All of this gear, simple, reliable, safe, and now relatively sabotage-proof.
So let's talk about electrics on this engine. Essentially, as part of a design-registered diesel engine system, there aren't any. This engine does not require any electronics or electrics to run. However, the vehicle generally does require electrics because, well, it's in underground coal. It's awfully dark down there without headlights. The alternator could be, and often is on loaders, hydraulically driven. So there's no electrics ever needed on the engine. But these engines have a mounting system that provides provision for alternators. This one is an MAE alternator, but there's also a mounting arrangement for PPKME mining repair alternators. So no electrics or electronics in the engine system itself, but there's provision for. Nice and simple. It's not an electronically injected engine, it's mechanical injection. Again, nice and simple, nice and cheap, and it avoids the problem of who's responsible for the engines and who gets to do the troubleshooting. Is it a mechanic or an electrician? That's a political issue in many underground coal mines. So it takes a lot more than just an engine shop to produce explosion-proof equipment. And EPEC's kindly allowed us to look behind the scenes at what it takes to make these things safely and reliably. We're going to go through some of the back rooms and some of the almost unique equipment they have to assist in the manufacture. Stay with us. A major part of any QA system is managing incoming goods, inwards goods, particularly inwards goods inspection. That's to make sure that you're getting what you've asked for, the old trust but verify. EPEC has a range of equipment to test those incoming parts, and sometimes it'll be a simple tape measure, verniers, micrometers and so forth. Sometimes it's a pressure test. Sometimes it's items like this electronically controlled drill. It's used to set speed sensors so that when the engine overspeeds, the sensor is able to shut the engine down. This unit in the corner is an oxygen index tester. It's used to test the flammability of materials, particularly things like fan belts. And it's the only way you can be sure that you've got, for example, a fire-resistant drive belt. And this little beast, this is a surface tester, surface roughness tester, and it's amazing. I'll show you a close-up. Here's a typical flange. I don't know whether it's intake or exhaust, but it's a typical flange. Normally we'd try and scratch the surface and compare it with a scratch pad, and that's very subjective. But with this device, we can turn it on and tell it to test. And right now it's graphing the results, and it will shortly give an absolute result. And that is 0.672 micrometers. So very, very smooth, and that's an absolute result, not a subjective one. And of course, if you're going to inspect components coming in, you need to be able to identify them. Sometimes by part number, sometimes by serial number if they're a controlled part. And there are lots of controlled parts on our flame-proof DES. In EPEC's case, they use either the laser engraver or the impact dot matrix engravers. This is a small portable unit. There's also a bigger unit that will identify and mark even stainless steel, which is notoriously hard to work with. So then we get to testing the fuel system components. The unit on the right tests the cracking pressure of injectors to make sure they're performing right in terms of pressure settings. And the yellow unit on the left is for checking spray patterns, so you can ensure between them that the injectors are working correctly and that the set for the engine is matched. And after the injectors comes the fuel pump. This is a fuel pump testing machine, and it allows accurate adjustment of the pump to calibrate where the fuel comes in, how much comes in, and to ensure again that the fuel pump itself is working right. With a calibrated fuel pump and tested injectors, you've got a fair chance of starting to control the emissions. So after you've tested all of those components, put them together and put them on the dyno, you need to start testing. Now you've seen the engine system on the dyno in the earlier scenes, but what you haven't seen is some of the test equipment that goes with it. And we start here with the dyno control. Then with all the data logging from the 14 different thermocouples and sensors that are on the engine just for dyno testing. That's in addition to the standard safety shutdown system. And then a variety of real-time emissions testing. 2 different types, and then there's even the MAHA up there for particulate measurements. This is what it takes to tune and design, certify a flame-proof diesel engine system for underground coal. ATEX doesn't have the requirements of emissions, but the data logging and dyno controls are still necessary. For underground coal, there's a lot of sophisticated equipment involved. Now, most of this is for what is called steady state testing. If it passes all the tests successfully here, the engine will go to another facility that has a dynamometer capable of testing to the UN regulations. And that's specifically, yes, there's a steady state test there too, but for transient cycle testing. That's where you're simulating the engine coming on load, load going off, speed changes, load changes, i.e. you're trying to simulate a real world condition. That's the hardest test to pass. And all of this equipment is predicated on getting the engine to the point where it can pass that test. There's a lot involved in testing this equipment. As I said earlier, it's beyond just being an engine shop. It's a very sophisticated arrangement. So this rather sad looking beast is a PPK mining equipment drift runner. It's primarily for personnel transporting in underground coal mines in Australia, although it has seen reasonable export success. It's a utility, or a pickup if you like, made to have different bodies fitted to the rear. Personnel, tray beds, cranes, all sorts of things. It's live axle front and rear. It has a coil suspension at all corners, and the engine you've seen inside is designed to go under this body, between these chassis rails and behind this grille. So they're the space constraints involved. This thing has power shift Clark transmission, Dana axles, and is ubiquitous in Australian mining. So this is the example. The engine on the dyno is configured for. Of course, it will fit other vehicles as well and can be adapted. But this is a typical vehicle in Australian underground coal mining. So that's what some flame-proof diesel engine systems look like. They are, in theory, quite simple, in practice, quite complicated. And the background behind them, well, you need a lot of help, you need a lot of special gear, and you need to know what you're doing. Our thanks today to EPEC for letting us come and film and visit. We've enjoyed it. We hope you have too. See you next time.